electric machinery exercises. Hello there, welcome to my channel. My name is Rafael. I am an electrical engineer, and in this video I would like to invite you to observe the solution of 8 exercises of DC machines and AC machines as a preparation for exams for electrical engineers. Let's go to the first exercise. Exercise number 1. A certain 5 horsepower 3-phase induction motor operates from a 440 volts RMS line-to-line 3-phase source and draws a line current of 6.8 amperes RMS at a power factor of 78%, lagging under rated full load conditions. The full load speed is 1150 rpm. Under no load conditions, the speed is 1195 rpm and the line current is 1.2 amps RMS at a power factor of 30%, lagging. Now the question: find the power loss and efficiency with full load and the input with no load, and the speed regulation. Okay, my friends, this is the exercise. Let's go to the solution. The exercise gave us this information for full load and for no load, my friends, and this is enough to calculate what the exercise wants us to calculate, and the exercise wants us to find the power loss and efficiency with full load and the input with no load and the speed regulation. Alright, let's go to the solution. The rated mechanical power, observed that the rated mechanical power is 5 horsepower, and converting it to watts we get the output power is equal to 5 horsepower times 746 watts per horsepower, and this is equal to 3730 watts, which can also be written as 3.73 kilowatts. Alright, my friends, this is the output power. As the exercise provided the RMS values of the voltage and current under full load conditions, we can calculate the input power. Observe that the exercise gave the line voltage and the line current, okay? Then we are going to calculate the input power as the input power is equal to the square root of 3, because we are working with line values, times 440 volts times 6.8 amps times the cosine of the angle. The cosine of the angle is this, 78%, lagging. Alright, then it is 0.78. okay, my friends, and then we find that the input power is equal to 4042 watts, which can be rewritten as 4.042 kilowatts. Okay, my friends, now we have the output power and we have the input power. Alright, the power loss is the difference between the input power and the output power. The power loss is equal to P in minus P out, and this is equal to 4042 watts minus 3730 watts, which is equal to 312 watts. Okay, my friend, this is the power lost in the machine. With these values, we can calculate the efficiency of the machine. The efficiency is equal to P out over P in times 100%, and this is equal to 3730 watts divided by 4042 watts times 100%, and we discover an efficiency equal to 92.28%. Okay, my friends, this is the efficiency of this machine. Okay, this is when it is operating with full load. Alright, now let's calculate similar parameters for no load. Okay, I'm going to erase here to calculate for no load. This is for full load. Let's calculate for no load. Under no load conditions, we are going to consider this. The input power is going to be equal to the square root of 3 because we are working with line-to-line voltages. Okay, this is a line voltage 440 volts RMS. 440 volts times the current at no load, 1.2 amps times the cosine of the angle. The exercise said that the power factor at no load is 30% lagging, then the power factor is 0.3. Okay, then the input power under no load conditions is 274.4 watts. And as we are operating under no load, the output power is 0. Okay, there is no load. Therefore, the power lost, P loss, is equal to P in, which is equal to 274.4 watts. Alright, my friends, and in this case the efficiency is 0. The efficiency is 0%. Okay? Now, to finish, let's calculate the speed regulation for the machine. The speed regulation is going to be the velocity at no load minus the velocity at full load divided by the velocity at full load times 100%, and this is equal to 1,100 here at no load first. Okay, no load 1195 minus 1150 divided by 1150, okay? And this times 100%, and this is equal to 3.91%. And this is the last result. The speed regulation of this machine is 3.91%. Alright, my friends, this is all for exercise 1. Let's go to the next. Let's go to exercise 2. Exercise number 2 now. Suppose that for the linear machine of the figure, B is equal to 1 Tesla, L is equal to 0.3 meters, Vt is equal to 2 volts, and R equal to 0.05 ohms. Letter A. Assuming that the bar is stationary at t equal to 0, calculate the initial current and the initial force on the bar. Also, determine the steady state speed, assuming that no mechanical load is applied to the bar. Letter B. Now suppose that a mechanical load of 4 newtons directed to the left is applied to the moving bar. In steady state, determine the speed, the power delivered by Vt, the power delivered to the mechanical load, the power lost to heat in the resistance Ra, and the efficiency. And finally, letter C. Now suppose that a mechanical pulling force of 2 newtons directed to the right is applied to the moving bar. In steady state, determine the speed, the power taken from the mechanical source, the power delivered to the battery, the power lost to the heat in the resistance Ra, and the efficiency. Okay, my friends, this is the exercise. Let's go to the solution. Let's begin with letter A. What does letter A want? Letter A says, assuming that the bar is stationary at t equal to 0, calculate the initial current and the initial force on the bar. Also determine the steady state speed, assuming that no mechanical load is applied to the bar. Okay, my friends, this is letter A. Let's go to the solution. Immediately after the switch is closed, the velocity is 0. For t equal to 0 plus immediately after the switch is closed, v, the velocity is equal to 0, okay? The bar is still stationary, and the induced voltage on the bar is equal to 0.2. EA is equal to 0, alright? The initial current is going to be for t equal to 0 plus the initial current for t equal to 0 plus is going to be equal to Vt divided by Ra, alright? Because immediately after the switch is closed, the bar is working as a short circuit. The only resistance is Ra, okay? And then we find Vt is 2 volts and Ra is equal to 0.05 ohms, and this is equal to 40 amps. This is the initial current. Okay, my friends? The resulting initial force on the bar is the force on the bar at T equal to 0 plus immediately after the switch is closed is equal to I times L vector B. Okay, this is one of the laws of induction, which is equal to ILB, which is equal to 40 amps. We just calculated the current, 40 amps. This length here is 0.3 meters, and the magnetic flux density is 1 Tesla, and this is equal to 12 newtons. This is the force on the moving bar when immediately after the switch is closed. Okay, my friends, now let's move on to steady state. In steady state, the bar is going to move to the right. Alright? In steady state with no load, the induced voltage equals the voltage of the battery. Okay? In steady state. In steady state with no load, the induced voltage equals the voltage of the battery. The induced voltage EA is equal to V vector B dot L, and this is equal to BLV, which is equal to VT. It has to be equal to the voltage of the battery. And solving for the velocity, V is going to be equal to VT over BL, and this is equal to 2 volts divided by 1 Tesla times 0.3 meters, and this is equal to 6.67 meters per second. Okay, my friends, this is all letter A wanted from us. I'm going to erase the board for letter B. Okay, let me clean this for letter B. What does letter B want? Let's read it again. Now suppose that a mechanical load of 4 newtons directed to the left is applied to the moving bar. In steady state, determine the speed, the power delivered by Vt, the power delivered to the mechanical load, the power lost to heat in the resistance Ra, and the efficiency. Alright, my friends, this is what we are going to calculate for letter B. Because the mechanical force opposes the motion of the bar, we have motor action. In steady state, the net force on the bar is 0. Thus, we obtain that the force is equal to B times I times L, which is equal to the force imposed by the load. Okay, my friends, solving this equation for the current, we know that IA is equal to F load divided by B times L, and this is equal to 4 newtons, because the exercise said that now suppose that a mechanical load of 4 newtons directed to the left is applied to the moving bar. So this force here is 4 newtons, and the magnetic field density is 1 Tesla, and the length here, the separation of the radius is 0.3 meters, and then we find 13.33 amps. Okay, this is the current. The exercise wanted us to calculate the current, determine the speed, in steady state determine the speed, the power delivered by VT, the power delivered to the mechanical load, etc. Alright, the induced voltage will be, okay, there is going to be an induced voltage here in the bar, okay, pointing upwards. Okay, this induced voltage is going to be equal to Vt minus Ra times Ia. Okay, Vt, we know it is 2 volts, and Ra we already know is 0.05 ohms, and the current we just calculated, and it is 13.33 amps. Okay, my friends, and then we find a voltage of 1.333 volts. Okay, now we can find the steady state speed. The exercise wanted us to calculate the speed in steady state. We can calculate it. We can calculate it by doing this. Okay. EA is equal to VBL, and solving for the velocity, V is equal to EA divided by B times L, and this is equal to 1.333 volts divided by 1 Tesla times 0.3 meters, and this is equal to 4.44 meters per second. Okay, my friends, this is the velocity in steady state. We have other things to calculate in letter B. The mechanical power delivered to the load. The mechanical power delivered to the load, PM, is equal to F load. Okay, the mechanical load of 4 newtons, which is going to be 4 newtons, and the velocity V, we just calculated the velocity, and then it is 4 newtons times 4.44 meters per second, and this is equal to 17.77 watts. Okay, the power taken from the battery, the exercise wanted us to calculate the power taken from the battery when in steady state. We are going to close this switch, and we are going to wait steady state to happen, and after steady state is reached, we want to know the power that the battery is delivering. Okay, and the power of the battery, P T, is gonna be equal to V T times IA. Okay, and VT is 2 volts, and the current IA is 13.333 amps, and this is equal to 26.67 watts. And the power dissipated in the resistance, it is easy to calculate the power dissipated in Ra. The power dissipated in the resistance, PR, is equal to Ia squared times the resistance, and this is equal to 13.333 amps squared times the resistance 0.05 ohms, and this is equal to 8.89 watts. And lastly, the exercise wants us to calculate the efficiency under this condition here. Okay, with a load of 4 newtons. The efficiency is going to be Pm over Pt times 100%, and this is equal to 17.77 watts divided by 26.67 watts times 100%, and this is equal to 66.7%. Alright, my friends, this is the efficiency of the machine under this load condition. Okay? And this is all for letter B. I'm going to clean the board for letter C now. Let's go to letter C. Let's read it again. Letter C says, now suppose that a mechanical pulling force of 2 newtons directed to the right is applied to the moving bar. In steady state, determine the speed, the power taken from the mechanical source, the power delivered to the battery, the power lost to heat in the resistance, and the efficiency. Okay, my friends, this is what the exercise wants from us, and we are going to do this. We are going to calculate this. With a pulling force applied to the moving bar, there's going to be a force here, a force applied to the right, okay? F. With a pulling force applied to the bar to the right, the bar speeds up, the induced voltage exceeds Vt, and the current circulates counterclockwise. Again, with a pulling force applied to the bar to the right, the bar speeds up, the induced voltage exceeds Vt, and the current circulates counterclockwise. Thus, the machine operates as a generator rather than a motor. In steady state, the force induced by the field is directed to the left and equals the pulling force. Therefore, F is equal to P times I times L, which is equal to the force of the pulling force. Alright, solving for the current, we have that IA is equal to F pull divided by PL. and this is equal to 2 newtons because the exercise said that this pulling force to the right is 2 newtons divided by 1 Tesla times 0.3 meters, and this is equal to 6.67 amps. Alright, my friends, the voltage along the bar will be the voltage here. This voltage here will exceed Vt, okay? So EA is equal to Vt plus Ra times Ia. Alright? And this is going to be equal to Vt 2 volts plus Ra is 0.05 ohms and Ia 6.67 amps, and this is equal to 2.33 volts. Okay, this is the voltage here induced by this pulling force. Alright, my friends, and observe that it exceeds Vt. Vt is 2 and EA is 2.33. With this information that we just found, with this information we can find the steady state speed. Okay, the steady state speed is going to be EA divided by B times L, and this is equal to 2.33 volts divided by 1 Tesla times 0.3 meters, and this is equal to 7.78 meters per second. Okay, the mechanical power delivered by the pulling force is equal to the mechanical power. PM is the mechanical power delivered by the pulling force is equal to the force times the velocity, and this is equal to 2 newtons. This force here is equal to 2 newtons, and the velocity we just calculated, it is 7.78 meters per second, and this is equal to 15.56 watts. Okay, this is the mechanical power delivered from the pulling force. Now the power absorbed by the battery, okay, as this induced voltage exceeds the voltage of the battery, in reality the current is going in the opposite direction. The current goes in this direction when there is no pulling force here, but when there is a pulling force, the current goes in the opposite direction and it is charging the battery. The power absorbed by the battery is PT is equal to the voltage of the battery times the current that is moving towards the battery, and this is equal to 2 volts times 6.67 amps, and this is equal to 13.33 watts. Alright, my friends, and the exercise wants us also to calculate the power dissipated in the resistance. It is easy. Okay, the power dissipated in the resistance is equal to the current squared times the resistance, and this is equal to 6.67 amps squared times the resistance, which is 0.05, and then we find that the power dissipated in the resistance is 2.22 watts. And lastly, the exercise wants us to calculate the efficiency under this condition, and the efficiency is going to be equal to Pt over Pm. Observe that this is the opposite. When there was no pulling force here, it was Pm over Pt. But now, as there is this pulling force and the current is going backwards, thus charging the battery, the efficiency is going to be in this way, times 100%, and this is equal to 13.33 watts divided by 15.56 watts times 100%, and this is an efficiency of 85.67%. Okay, my friends, this is all the exercise wanted. Exercise 2 wanted us to calculate this. Let's move on to the next. Let's go to exercise number 3. Exercise number 3 now, my friends, DC machine performance calculations. The machine having the magnetization curve of the figure is operating as a motor at a speed of 800 RPM with IA equal to 30 amps and IF equal to 2.5 amps. The armature resistance is 0.3 ohms and the field resistance is 50 ohms. The question: find the voltage VF applied to the field circuit, the voltage VT applied to the armature, the developed torque, and the developed power. Okay, my friends, this is the exercise. Let's go to the solution. It is possible to calculate the voltage of the field producing branch using RF and IF. Okay, we are going to calculate the voltage of the field producing branch using RF and IF here. All right, VF is equal to RF times IF, and this is equal to 50 ohms times 2.5 amps, and this is equal to 125 volts. Okay, why did I only use the resistance? Why did I not use the inductance? Because inductances in steady state behave as short circuits. Okay, then we are considering this inductance here as a short circuit, and we are only considering for the calculation the resistance. Alright, so it is possible to calculate the voltage of the field producing branch using the resistance RF and the current IF, and this is what we did. From the magnetization curve, we see that IF is 2.5 amps. The induced voltage is EA 145 volts. Okay, this is the magnetization curve for this machine, and 2.5 amps corresponds to a voltage of 145 volts. Okay, and the speed is 1200 RPM. Alright, for the speed of 800 RPM, we will use the following. This is a linear relationship because there is a part of the graph that can be considered linear and the other part saturates and cannot be considered linear. We are operating under the assumption that this part here can be considered linear, alright? If this is a linear relationship, then A1 divided by A2 is equal to the velocity 1 divided by the velocity 2. And solving for EA2, we find that EA2 is equal, we just substitute the values, okay? 1200 RPM here, 800 RPM here, and here we put 145 volts, okay? So it's gonna be the velocity 2 divided by the velocity 1 times EA1, and this is equal to 800 divided by 1200 times 145, and this is equal to 96.67 volts, okay? This is this value here. Alright, from the magnetization curve we see that IF is 2.5 for the induced voltage of 145 volts at the velocity of 1200 RPM. And using this linear relationship, we found that EA2 is equal to 96.67 volts. Okay, my friends? The machine speed in radians per second is, we are going to convert 800 to radians per second. Okay, Wm is going to be equal to 800 RPM times 2 pi radians divided by 60 seconds, because revolutions per minute, RPM means revolutions per minute, and in 1 minute we have 60 seconds, and this is equal to 83.78 radians per second. Okay, my friends, this is the velocity in radians per second. The expression for the induced voltage is, we have that the expression for the induced voltage is E. A is equal to K times phi times Wm, and if we solve for this parameter here, we find that K times phi is equal to EA divided by Wm, which is equal to 1.154, okay? To find the developed torque, we use the expression for the developed torque. And the expression for the developed torque is equal to tau is equal to K times phi times IA, okay? And we already know the value of this parameter here, and it is 1.154 multiplying IA, and IA is 30, okay? The exercise gave this value, IA is 30 amps, okay? And this is equal to a torque of 34.62 Newton meters, okay? This is the torque developed by the machine, okay? Alright, I'm going to have to erase this because we are going to need to calculate more things, okay? Our last result is that the torque developed under this condition, 800 RPM, is 34.62 Newton meters, alright? Now the developed power is gonna be the developed power. The power is gonna be equal to the mechanical velocity in radians per second. No, in RPM, sorry. The velocity in RPM times the torque that we just calculated, and this is equal to 2,900 watts, which is also equal to 2.9 kilowatts. Okay, you simply multiply the velocity in radians per second. We found a velocity of 83.78 radians per second, and you multiply by the torque, and we found a torque of 34.62 Newton meters. And if you carry out this multiplication, you're gonna find 2.9 kilowatts. Alright, my friends, which can be calculated also by using the electrical quantities. Okay, P is equal to IA times EA. Here we use mechanical quantities, here we are using electrical quantities, and using electrical quantities we can also calculate and find the same value, 30 amps times 96.67 volts, and this is also equal to 2.9 kilowatts. Alright, my friends, and applying KVL on the armature circuit, we find that VT is equal to RA times IA, okay, RA times IA, it's the voltage, current times resistance is voltage, plus the induced voltage E. And this is equal to 0.3 ohms times the current 30 amps plus the induced voltage, which is 96.67 volts, and the terminal voltage VT is equal to 105.67 volts. Okay, my friends, this is the last result of exercise number 3. Alright, is everything okay? And this is all for exercise number 3. Let's go to exercise number 4 now. Exercise number 4, my friends. A 50 horsepower shunt-connected DC motor has the magnetization curve as shown in the figure. The DC supply voltage is 240 volts. The armature resistance RA is 0.065 ohms. The field resistance RF is 10 ohms, and the adjustable resistance is R adjust equal to 14 ohms. At a speed of 1200 RPM, the rotational loss is P-rod 1450 watts. The question: if the motor drives a hoist that demands a torque of T out equal to 250 Newton meters independent of speed, determine the motor speed and efficiency. Okay, my friends, this is the exercise. Let's go to the solution. From the circuit we can find that the field current is, the field current IF is equal to VT divided by R adjustable plus RF. Okay, why did I not count with the inductance? Because the inductance in steady state is a short circuit, okay? So we need to just use the adjustable resistance and the field resistance, okay? And this is equal to 240 volts divided by 10 ohms plus 14 ohms, and this is equal to 10 amps. Alright, the field current is therefore 10 amps. Next, we use the magnetization curve to find the machine constant K phi. We need to find K phi, okay? This constant here is important for us, and we are going to use the magnetization curve to find this constant, okay? We are going to assume that from this to this, the curve is approximately constant, okay? There is saturation and it loses constancy, but we are going to assume that from 0 to here the curve is approximately constant, and this proportionality holds true. Alright, from the curve we see that the induced armature voltage is E. A is equal to 280 volts for the velocity of 1200 rpm, and this makes a for the current of 10 amps, okay? We calculated a field current of 10 amps, and corresponding to this is a voltage, an induced voltage of 280 volts. Alright? We are going to use this information, thus using the expression that says that EA is equal to K times phi times WM, and we solve for this, we find that K times phi is equal to 280 volts divided by this, okay? This is equal to this, but converted to radians per second. It is going to be 1200 rpm times 2 times pi divided by 60 seconds, because this RPM means revolutions per minute, and in 1 minute we have 60 seconds, okay? And then this is equal to 2.228, okay? This is a constant, and we are going to use this constant, okay? Alright, I am going to clean the board because we are going to need to calculate more things. We assume that the rotational power loss is proportional to speed. This is equivalent to assuming constant torque for the rotational loss. The rotational loss torque is equal to the rotational power loss, okay, divided by Wm. Again, we are going to convert it to radians per second, and this is equal to 1450 watts. The exercise provided this information here, that the rotational losses amounted to 1450 watts, and it is going to be 1200 rpm, 2 pi over 60 seconds, and this is equal to 11.54 Newton meters. We are losing this amount of torque, okay? Thus, the developed torque, we are going to calculate the developed torque. the developed torque. The torque developed. The developed torque is going to be equal to the output torque. The output torque is the torque that actually goes to the load, plus the torque loss due to rotational losses. Rot. And then the developed torque is 250 Newton meters plus 11.54 Newton meters, and this is equal to 261.5 Newton meters. Okay, this is the developed torque. Alright, and I'm going to erase again the board because I'm going to need more space for more calculation. Okay, my friends? Alright, to find the armature current, we use that the developed torque. The developed torque is equal to K times phi times IA. Do you remember this constant that we calculated? And we found a value of 2.228. So solving for IA, we find that it is equal to 261.5 Newton meters divided by the value of this constant here, which is 2.228, and this is equal to the current 117.4 amps. Okay, IA is this current here that goes to the load. Alright, this is IF, this is IA. Okay, applying KVL on the armature circuit, we find that, EA is equal to VT. Okay, EA is equal to VT minus IA RA, minus IA RA. Okay, this voltage here plus this voltage drop here is equal to the voltage from here to here. Okay, and we use the values. The terminal voltage is equal to 240 volts minus RA equal to 0.065 ohms, and the current we just calculated, it is 117.4 amps, and then the induced voltage, the voltage on the armature, is equal to 232.4 volts. Okay, my friends, we have not yet finished. We have more things to calculate for exercise number 4. I'm going to have to clean it again for more calculation, my friends. Okay, now using that EA is equal to K times phi times Wm, and solving for the speed, okay, solving for the speed, we find that Wm is equal to EA over K phi. This constant is important, that's why we calculated it first, and this is equal to 232 2.4 volts divided by 2.228, and this is equal to 104.3 radians per second. Okay, we are going to convert from radians per second to RPM, and to do this it is simple. The mechanical speed is going to be equal to Wm times 60 seconds divided by 2 pi, and this is equal to 996 RPM, or revolutions per minute. To find the efficiency, we firstly compute the input and the output power. Okay, we need to compute the input and the output power first to calculate the efficiency. The output power can be calculated as the output torque, okay, times the output velocity, the velocity of the shaft, which is 250 Newton meters, times 104.3 radians per second, okay, and the output power is equal to 26.08 kilowatts. All right, and how about the input power? The input power is equal to the terminal voltage times the current IL. Okay, this is the input power. Take a look at this. The voltage here, the terminal voltage, times this current here, IL. IL goes, part of IL goes to the field and part of IL goes to the load. Alright? And IL is equal to IF plus IA. We already know then, we already know IF and we already know IA. So it is going to be equal to VT times IF plus IA, and this is equal to 240 volts times 10 amps plus 117.4 amps, and then our input power is going to be equal to 30.58 kilowatts. Okay, and consequently, this is the last result. Consequently, our efficiency is equal to P out over P in times 100%, and this is equal to 85.3%. Okay, my friends, this is all for exercise number 4. Let's go to exercise number 5 now. Exercise number 4, my friends, series connected DC motor. A series connected DC motor runs at a speed of 1200 RPM while driving a load that demands a torque of 12 Newton meters. Neglecting resistances, rotational losses, and saturation effects, find the output power. Then find the new speed and output power if the load increases to 24 Newton meters. Okay, my friends, this is the exercise. Let's go to the solution. Since we are neglecting the losses, the output torque and the power are equal to the developed torque and power respectively. Okay? Alright, the exercise wants us this. find the output power, then find the new speed and output power if the load increases to 24 Newton meters. But the exercises say that neglecting resistances, rotational losses, and saturation effects. Alright, firstly, let's calculate the angular speed. Wm1 is equal to Nm1 times 2 pi over 60 seconds. We are simply converting from RPM, revolutions per minute, to radians per second. And you have to bear in mind that in 1 minute there are 60 seconds, okay? And then we find 125.7 radians per second. Okay, my friends, and the output power is equal to the developed power because we are neglecting losses. Then the developed power is equal to the output power 1, which is equal to the velocity 1 in radians per second times the torque 1, and this is equal to 1508 watts. Okay, my friends, this is the first result. Since we are considering that RA and RF are equal to 0, we are considering this. The exercise requested us to consider this. RA and RF equal to 0, okay? And since we are considering this, the equation for the torque can be simplified. We have an equation for the torque like this. The developed torque is equal to K times Kf times Vt squared divided by Ra plus Rf plus K plus times K times Kf Wm squared, okay? This gigantic expression here. But since we are considering that Ra is equal to Rf equal to 0, we are going to simplify this expression here into Vt squared divided by Kf Wm squared. Okay, we are going to work with this simplification in which this constant here, Kf, is a constant that depends on the number of field windings, okay? And how about this other K here? This other K here, we know that the EA is equal to K times phi times Wm. Alright, this K here is this K here, and Kf is a constant that depends on the number of field windings. Alright, and since phi is equal to Kf times Ia, we obtain the expression above, okay? We obtain the expression above. Thus, for a fixed supply voltage Vt, torque is inversely proportional to speed squared, and we can write this, okay? This proportionality here holds true. The developed torque 1 divided by the developed torque 2 is equal to Wm2 squared divided by Wm1 squared. Okay? Solving for Wm2, we find that Wm2 is equal to Wm1 times the square root of the developed torque number 1 divided by the developed torque number 2, and this is equal to this is 125.7 radians per second. Here 125.7 radians per second. This is 12, okay, number 1, and this is 24, number 2. And then we find that this velocity here, number 2, is equal to 88.88 radians per second. Alright, we are almost finishing, and this corresponds to a speed in RPM equal to 848.5 RPM. Alright? Finally, the output power with the heavier load. The output power with the heavier load is, we can calculate it like this, P out, using mechanical quantities. We are not going to use electrical quantities, we can use mechanical quantities, and this is equal to the developed power, the developed torque. It is equal to the developed torque times the rotational speed in radians per second, and if you use the values, you're gonna find that the output power is 2133 watts. Okay, my friends, this is all for exercise number 5. Let's go to the next. Let's go to exercise number 6. Exercise number 6 now, my friends. Induction motor performance. A certain 30 HP 4-pole 440 volts 60 Hz 3-phase delta connected induction motor has the following parameters. The exercise provided this data here. Under nominal load, the machine operates at 1746 RPM and has rotational losses amounting to 900 watts. The question: find the power factor, the line current, the output power, the copper losses, the output torque, and the efficiency. Okay, my friends, this is what the exercise wants, and let's go do it. Let's calculate. We know that the synchronous speed of a 4-pole induction motor is, okay, the synchronous speed of a 4-pole induction motor is 1800 RPM, okay? Then it is possible to calculate the slip based on this. The slip is equal to the synchronous speed minus the working speed divided by the synchronous speed. Okay, and this, in the place of this, I put 1800 RPM, In the place of this, I put 1746, and here I put again 1800 RPM, and then we find a slip equal to 0.03. Okay? The impedance seen by the source is, let's calculate the impedance seen by the source. We are going to work with equivalent impedances. Okay, let's bundle these guys up. Let's bundle this guy with this guy, okay, and call it equivalent impedance number 1. Okay, it is going to be equal to this plus this, okay. This, the exercise said, it is 0.6 ohms plus, with the value of the slip, we can calculate this resistance here, and it is equal to 1 minus 0.03 divided by 0.03 times this, okay, times 0.6, and then we find it to be equal to 20 ohms. All right, this is in series with this inductance here, and we are going to call it the equivalent impedance number 2. ZAC2 is going to be equal to 20 that we just calculated, plus this reactance here. The exercise said it is J 0.8 ohms. All right, now we have the parallel connection between this, the magnetization reactance, with all this, all that we just calculated. Then it is the equivalent impedance number 3 is going to be J50. Okay, the exercises say that the magnetization reactance is J50, and this is going to be in a parallel connection with 20 plus J 0.8 ohms. Okay, this thing here means parallel connection. All right, and this substitutes all this, okay. This here, equivalent impedance number 3, substitutes all this, and this is going to be in series with this, okay. So it is going to be the total equivalent impedance is going to be equal to 1.2 ohms plus J2 plus the parallel connection between J50 and 20 plus J 0.8 ohms. Okay, it's simple mathematics. All right, you're gonna need to work with complex numbers. It is simple mathematics, okay, and we find that this, the total equivalent impedance, the impedance seen by the source, is equal to 17.97 plus J 9.4, which is equal, this is the Cartesian representation. We are going to transform it to polar, and in polar it is 20.28 in the phase, 27.59 degrees ohms. All right, we calculated this because we need it, especially the angle. We're gonna need to work with this angle. Okay, I'm gonna clean the board because I'm gonna need some room for more calculation. Just wait a minute. All right. All right. The power factor, that's why we calculated the angle. Okay, we converted from the Cartesian to the polar form because we needed the angle. The power factor is the cosine of the angle of the impedance. The power factor is equal to the cosine of the angle, 27.59 degrees, and this is equal to 88.63% lagging. Alright? It has to be lagging because it is an induction motor. For a delta connected machine, the phase voltages are equal to the line voltages. Alright? It is important to know this. For a delta connected machine, the phase voltages are equal to the line voltages, which were specified as 440 RPM. There's information in this. Okay, for a delta connected machine, the phase voltages are equal to the line voltages, and they are equal to 440 RMS. All right, 440 RMS. And the phase current is simply the division. The phase current is simply the division between the phase voltage by the impedance. Okay? And the impedance seen by the source. And this is equal to 440 phase 0 degrees volts divided by 20.28 in the phase 27.59 degrees ohms. Okay, and with this we find the value of the phase current, which is equal to 21.7 in the phase negative 27.59 degrees amps. Okay, this is the value of the phase current. Thus, the magnitude of the line current, okay, this is the characteristic of the delta connected machine. The phase voltages are equal to the line voltages, but when it comes to current, they are not equal. Okay, the line current I line is equal to the square root of 3 times the phase current, and this is equal to 21.7 times the square root of 3, and this is equal to 37.59 amps RMS. Alright? We need the RMS values to calculate the power. We don't calculate power with peak values, we calculate power with the RMS values. So let's calculate the input power. The input power P in is equal to 3 times the phase current times the phase voltage times the cosine of the angle, okay? And this is equal to 3 times 21.7 amps times 440 volts times the cosine of the angle, which is going to be the cosine of 27.59 degrees. Alright, computing this, it is easy. We find that the input power is 25.38 kilowatts. Alright, my friends, this is the input power. Now we are going to calculate this Vx. Alright, let's calculate Vx. I'm gonna clean here again for more room. Vx is equal to Is, the current of the source, times the equivalent resistance, the equivalent impedance that substitutes all this. We calculated it, okay? And we called this equivalent impedance number 3. If you go back, you're gonna see that we called it equivalent impedance number 3. Okay, so Vx is going to be the current of the source times the equivalent impedance number 3, and this is equal to Is times J50 in a parallel connection between 20 plus J 0.8, okay? And substituting the values, okay? We have already calculated everything. We know that Is is 21.7 in the phase negative 27.59 degrees. This here, okay, can be easily calculated. You simply calculate the parallel connections between these guys here, alright, and then we find the value of Vx equal to 397.8 in the phase negative 3.807 degrees volts RMS. Okay, we are working with RMS values. All right, now let's calculate the current. Let's calculate the current. The current IM. The current here. The current here. This current here. Let's calculate this current here. IM prime. Alright, we are going to calculate this current here. This current here, I m prime, is equal to Vx divided by 0.6 ohms plus 19.4 ohms plus J 0.8 ohms, okay? And this is equal to, we simply substitute, okay? We just calculated the value of Vx, we put the value of Vx and we divide by this, okay? It's simple mathematics, and we find that the value of this current here is equal to 19.88 in the phase negative 5.52 degrees amps RMS. All right. The copper losses in the stator and the rotor are. We are going to calculate the copper losses in the stator. The copper losses in the stator is going to be equal to this S means stator. Okay. All right. The copper losses in the stator is going to be 3 times Rs times the current squared. This is the current of the source, and this is the copper losses in the stator. Okay, I use the same letter here, but don't confuse it. This is the current in the stator, and this is the copper loss. This is the current of the source, and this is the copper losses in the stator. Okay, and this is equal to 3 times 1.2 ohms times 21.7 amps squared, and this is equal to 1695 watts. Alright, now let's calculate the copper losses in the rotor. The copper losses in the rotor will be equal to 3 times R prime times I m prime. Okay, we are going to use this current here squared to calculate the rotor copper losses, and it is going to be equal to 3 times 0.6 ohms times 19.88 amps squared. We just calculated the value of this current here, and this is equal to 711.4 watts. Alright, my friends, these are the copper losses in the stator and in the rotor. Now let's calculate the developed power. The developed power is equal to 3 times 1 minus S over S times R m prime times I m prime squared, which is equal to, if we use the value of the slip, we calculated and we found 0.03. Okay, you put the value of the slip here, and it is equal to 23 kilowatts. Okay, my friends, we are almost finishing exercise number 6. I'm going to have to clear the board again for more calculation. Okay, the output power is equal to the developed power minus the rotational losses. Alright, the power that goes to the load, the output power, is equal to the developed power minus the losses, the rotational losses. Okay? The output power is equal to the developed power minus the rotational losses, and this is equal to 23 kilowatts minus 0.9 kilowatts, and this is equal to 22.1 kilowatts. This corresponds to 29, and this here corresponds, if you convert, corresponds to 29.6 horsepower. Okay, this corresponds to 29.62 horsepower. So the motor is operating very close to its rated load of 30 horsepower. Okay, the output torque is equal to the output power divided by the velocity in radians per second, and it is equal to 22.1 kilowatts divided by 1746 RPM. This is in RPM. I'm going to convert it to radians per second using this conversion factor here, and I found that it is equal to 120.6 1.9 Newton meters. Okay, this is the output torque. At last, finally, at last we calculate the efficiency of the machine. The efficiency of the machine is equal to P out divided by P in times 100%, and this is equal to 22.1 kilowatts divided by 25.38. 25, I forgot the number, sorry. It was 25.38 kilowatts multiplying 100%, and finally we find that the efficiency of this machine is 87%. Okay, my friends, this is all for exercise number 6. Let's go to the next. Let's go to exercise number 7. Exercise number 7, my friends, the starting current and torque of an induction motor. The exercise wants us to calculate the starting line current and torque for the motor of the previous exercise. We are going to work with the same motor we worked with in exercise 6, but now we are going to pay attention on the starting conditions, okay? For starting from a standstill, we know that the slip is equal to 1, okay? When the slip is equal to 1, this resistance here is equal to 0, okay? 1 minus 1 is equal to 0, alright? Then the equivalent circuit when the slip is equal to 1, that is at starting, is equal to 0. Okay, this resistance is equal to 0, and the equivalent circuit is this. Alright? Now let's bundle some things together. We are going to bundle these resistances here together, and we are going to call it their equivalent resistance, and this is going to be JXM in a parallel connection between R prime plus JXR prime. Alright? And if we use the values, we find that this is equal to 0.5812 plus J, 0.7943 ohms, and we are calling this the equivalent resistance plus J, the equivalent reactance, okay? And the circuit becomes this circuit here. We are going to rewrite this circuit in a different way, okay? Let me erase here, and I'm going to show you how the circuit is going to become, alright? We are going to have the circuit like this. We are going to have here the equivalent resistance and here the equivalent reactance, and this is valid only for the starting condition at starting of the motor, okay? The impedance seen by the source is equal to, let's calculate the impedance seen by the source. It is going to be equal to 1.2 ohms plus J2 ohms plus the equivalent impedance, okay, which is the combination of these two, and we find that it is equal to 1.7812 plus J 2.793 ohms. This is the impedance seen by the source. Okay, and this is in the Cartesian representation. We are going to convert it to polar. Converting it to polar, we find that it is 3.314 in the phase 57.48 degrees ohms. Okay, thus the starting phase current is this. We are going to calculate the starting phase current IS at t equal to 0 plus is going to be equal to Vs. Okay, this is Vs divided by the impedance seen by the source that we just calculated, and this is equal to 440 phases 0 degrees volts divided by 3.314 phase 57.48 degrees ohms, and this is equal to 132.8 in the phase negative 57.48 degrees amps RMS. This is the starting current. Okay, the starting phase current. Okay, as the motor is delta connected, the phase voltages are equal to the line voltages, but it doesn't happen with the currents. The line current is equal to the square root of 3 times the phase current. So the line current I line is equal to at starting conditions, okay, is equal to the square root of 3 times IS that we just calculated here at starting condition, and this is equal to 230 amps RMS. Alright, my friends, and to calculate the torque, the starting torque, we need the power at the air gap. The power at the air gap, PAG, is equal to 3 times the equivalent resistance times the phase current at starting condition, okay, squared, and this is equal to 30.75 kilowatts. This is the power at the air gap. And finally, we are going to use this expression here. PAG is equal to the torque developed times the speed in radians per second. And if we solve for the torque, we find that the developed torque is equal to 30.75 kilowatts, 30,750 watts, which is also 30.75 kilowatts, divided by 2 pi 60 divided by 2, and this is equal to 163.1 Newton meters. Okay, my friends, and this is all the exercise wanted from us. Let's go to the last exercise, my friends. Let's go to exercise number 8. Let's go to the last exercise, my friends. Let's go to exercise number 8. Induction motor performance. A 220 volts RMS, 60 Hertz, three-phase Y-connected induction motor draws 31.87 amps at a power factor of 75% lagging. For all three phases, the total stator copper losses are 400 watts and the total rotor copper losses are 150 watts. The rotational losses are 500 watts. With this data, find the power crossing the air gap, PAG, the developed power, PDEV, the output power, Pout, and the efficiency. Okay, my friends, this is the exercise. Let's go to the solution. We are going to calculate what the exercise wants based on this information that the exercise provided. Alright, for a Y-connected induction motor, the phase voltage is Vs. We are going to call this phase voltage is equal to the line voltage divided by the square root of 3. Okay? And this is equal to 127 volts RMS. Alright? The line voltage is 220 volts RMS and the phase voltage is 127 volts RMS. Alright? Next we find the input power. We have everything to find the input power. We're gonna find the input power like this. The input power is equal to 3 times the phase voltage times the phase current times the cosine of the angle. Okay? The input power is equal to 3 times the phase voltage. We just calculated it. It is 127 volts. Remember that whenever calculating power, we have to use the RMS value of the voltage and the current, never the peak value, okay? And the current is 31.87 amps, and the power factor is 75% lagging times 0.75, and then we find that the input power is equal to 9,107 watts. Alright, my friends, the air gap power is the input power minus the stator copper losses. Okay? PAG is equal to P in the input power minus the stator copper losses. Okay? And this is equal to 9,107 watts minus 400 watts. And this is equal to 8,707 watts. Okay? The developed power is the input power minus the copper losses. The developed power is equal to the input power 9,107 watts minus the all copper losses, the stator copper losses and the rotor copper losses. 400 watts minus 150 watts, and this is equal to 8,557 watts. Okay, my friends, next, by subtracting the rotational losses, we find the output power. The output power, P out, is equal to the developed power minus the rotational losses. Minus the rotational losses. And this is equal to 8,557 watts minus 500 watts. and this is equal to 8057 watts. And with this data, we can calculate the efficiency of the machine. The efficiency of the machine is equal to P out over P in times 100%, and then it is equal, you just substitute, we have P in, we already calculated P in, P in is this, P out is this, and then we substitute the value and find that it is 94%. Okay, my friends, this is all for exercise 8, and this is all for this video. I hope you enjoyed it and learned from it. I am a teacher, guys. If you want to book a lesson with me, use my WhatsApp number. Goodbye.